So, good afternoon, everyone. Today we'll be completing with the Ethereum basics and then start with solidity programming. So, in the last class, we were talking about the block header. So, when we're talking about the Bitcoin blockchain had a very simple block header, which is that you have the parent hash, you have the timestamp, you have the Merkle root hash, you have block hash, nonce, list of transactions, and the transaction counter. But here, if you look at the Ethereum block header, you can see that we have a lot of fields. So 15 fields are available here in this Ethereum block header. So there are some fields that we are familiar with. That is, we know what a parent block hash is. We know what a nonce is. We know what a timestamp is. We know the difficulty target. And this number means the block number. That is, this number is the block number. So let us quickly see all of these block headers one by one. So block fields, sorry. So let us see all of these block fields one by one. So all transactions that are grouped together form a block. And blockchain is a series of such blocks that are chained together. So you can say that a block contains a summary of all of the transactions, either whether it is like a ether transfer transaction or it is a transaction to initiate a smart contract. So in Ethereum, a block consists of the block header, the information about the set of transactions that are included in that block, and we have a set of other block headers for the current block's owners. So previous class we had left with Omer hash. We did not talk about this Omer hash. So let us first see what this Omer's hash is. That is, what exactly is the Omer's hash. So in Ethereum, the time taken for building a block is very small. That is, if you take an average time that is required for building a block, it is around, say, 7 to 15 seconds. And if you compare it with other blockchains, like the Bitcoin blockchain, the time required for a block generation is 10 minutes. So even though the block generation time is very small in Ethereum, it leads to faster transaction processing. However, there is one downside of the shorter block time. So there is one downside to the shorter block time. Let us see what the downside is. So I'm sharing this board here. So if you look at this board, so say there are, you have a blockchain which consists of a series of blocks. All right, you have a series of block. You call this block as, say, block, let us start with block 12. This is block 13. This here is block 14. This here is block 15. And this here we have is block 16. And each of these block is linked to the previous block. All right. And this is done using the parent block hash. So every block has its parent's block hash. And we are saying the block generation time in Ethereum is between 7 to 15 seconds. So let us consider this as 15 seconds. So it means that every 15 seconds, a new block is generated. So even though it enables faster transaction processing, there is a downside to it. And the downside is that it may happen, suppose this time instance is t equal to 0. The time is at say not t0, at time say the nth time. It may happen that at this time instant 4 blocks are mined. At say 12th second or whatever timestamp is, right now it is 12:40 p.m. So say at 12:40 p.m. following 4 blocks are mined. So because the block generation time is very small, it may happen that at the same very second, a lot of blocks are mined. That is, if you look at our example here, we are seeing that 4 blocks are mined at the same time. You can see that 4 blocks are mined at the same time. Okay. And these competing blocks are referred to as orphan blocks. Okay, so what will happen now is, see, these were mined. It may happen that you have several miners on your network. Some miner builds this chain. Okay, say miner 1. Some miner builds this chain. Some miner builds this chain and other miner builds this chain. So we have different miners who are building their chain. All right. Now, if you see here, this leads to ambiguity in the network. That is, we have 4 blocks that were able to find a nonce which was less than the difficulty target, and they were able to link to the previous block in the chain. Now, what will happen now is, it may happen that a miner, we have a miner that links to this chain, or it may happen that we may have a miner that links to this chain. All right, that is, so you can see right now we have different chains on the network. If even if we consider this will be can be our chain 1 and this can be our chain 2. Now exactly what happens here is, if you remember in Bitcoin, we follow the concept of longest chain. That is, miners will switch to the chain on which maximum computation has been done, that is maximum proof of work has been done. So if you look at our example here, it is very easy to tell that this chain is the maximum or the longest chain in the network. Now what will happen is, this chain, this chain, and this chain, these chains are abandoned. All these chains are abandoned, and what happens is they become orphans. So they become orphans. So this now becomes our longest chain, and all of these become the orphans. So omers are the stale blocks that are not part of the main chain. Even though they were mined, they are not part of the final selection which makes the Ethereum blockchain. So you can think of omers as uncle blocks or stale blocks that have no parent. So if you look at this example here, they have no parent. They are abandoned blocks. All right. So these blocks have no parent. And what Ethereum network has done is that now see, these are abandoned blocks. So what Ethereum network does is it provides you or provides the miner with an incentive for including these blocks first. So these are blocks, they will have some transactions inside of them. So what the Ethereum blockchain does is that these blocks are abandoned blocks. Their transactions are reverted. They did not make part, they did not like get added to the main blockchain here. So what the Ethereum network does is that it allows the miners, like it rewards the miner for including these orphan blocks. Okay. So, and they will like they will get some reward for adding the block to the blockchain. So if you include the orphan block, if you include the orphan block, then there is incentive for the miner. Now this incentive is not same as that you receive when you mine a new block, but still you get an incentive. Okay. So the root hash of all the transactions in the Omer's block is known as the Omer's hash here. Okay. So this is Omer's hash. So we know what a parent hash is. So parent hash is the hash of the parent block's header. And this is what makes the block a set of chain. Then we have Omer's hash, which is the root hash of the list of Omers that have been included in your block. Then there is beneficiary. Beneficiary is the account address which will receive the fee for mining this block. So beneficiary means the account address or the Ethereum address of the miner. Then we know that we have three fields here: the state root, the storage root, and the transaction root. The state root is the root node of the state triad. Then we have transaction root, which stores the list of all the transactions. And then we have a storage root, which consists of all the data that is stored on your blockchain. Then we know what a difficulty is. Number is the count of the current block. We know what gas limit is. Gas limit is set by the network. That is, even though the sender of the transaction sets the limit, but it is dictated based on the trend that is going on the network. So what amount of ether will a miner receive for verifying a transaction or including that transaction in his block? So these are the fields of the block header. All right. So if you look at this website here, which is known as Etherscan will also give you the latest blocks here on the Ethereum blockchain. So it shows that the latest block mined is this block, which was mined 27 seconds ago, and it will give you the name of the miner. Here you see that this is a pool, that is, you have a group of miners who are splitting their reward, their computation power, mine the block, and it tells us the number of transactions that are included in this block. So there are 55 transactions, and it will also tell you the type of transaction, whether it is a like a value transfer transaction or a contract transaction, and it will give you the amount of time required for mining the block. So if you click it here, it will give you the all the fields that we have studied here. Okay, it will give you who mined the blocks, and here it shows there are 55 transactions, and there are 21 contract internal transactions. Okay, that is 21 transactions have been created to initiate the contracts. It gives you the size, the total difficulty, and the gas used. So here you can see it says the gas limit is set as this number. But the gas used is only this. So remember we were talking about that you set your gas. So gas was set at this number, but only 16.5% of it was used and rest of it was returned back to the sender or the initiator of the transaction. So these are the block fields that are present there. There is also a field called extra bit, which gives you extra data, which gives you some information regarding the miner or the mining pool that has been used to perform the transaction. So these are all the fields that are present in the block header. Next, we'll talk a bit about how transactions are verified in the Ethereum blockchain. Okay, so we know that we have a Merkle tree which is used for verifying the transaction. So if you look at this figure here, so we know that we make use of a Merkle tree to verify the transactions. So suppose there is, say, 30 transactions present in your blockchain. So in Ethereum, there are two types of nodes. There are full nodes and there are lightweight nodes. Okay. So full nodes are minor nodes that need to have the complete copy of the Ethereum blockchain because they want to know the entire history of blockchain because they will be including transactions, and before including transactions they have to ensure that the transactions are not double spent. They have to verify. So full nodes are the special nodes or the minor nodes, but there are other lightweight nodes also. So what the lightweight nodes do is they do not have the complete, you can say, the copy of the Ethereum blockchain. What they will do is they will only have a copy of root hashes. Okay, they will only have a copy of the root hashes of the transactions instead of having the entire, you can say, the blockchain. So again here in Ethereum, we make use of a Merkle tree. So what the lightweight nodes do is they don't store the complete history of transaction, but they only store the, you can say, the root hashes of the transactions. Okay, so and with the help of the root hashes, you can verify whether the transactions have been changed or not. So if you had to verify this field here, okay, so you know that suppose you changed something here. So this will change, this will change, this will change, and this will change, right? And instantly it will give you an error that if you hash these two together, you are not definitely getting this. And since this value is false, this value itself will become false. And finally, your root hash gets invalidated. Root hash as in different. Now, all of these are root hashes. And you're using them to validate transaction. And if you like change even one root hash, the entire hash changes. So this is the concept of full nodes and light nodes. Full nodes contain everything regarding a blockchain, but light nodes have like a lesser information storing only the root hashes. So this is the block header and this is how the information is stored. Now, this is all there was with respect to Ethereum blockchain. We'll now start with Solidity programming. So Solidity is an object-oriented high-level language which is used for implementing smart contracts. That is, if you are wanting to implement smart contracts, you need to use Solidity, which is the language for writing smart contracts. And Solidity is statically typed. So by statically typed, we mean that a statically typed language is a language where variables should be known at compile time. So your languages like Java or C or C++, all of them are statically typed languages. You have to make your declarations so that at compilation, your compiler knows all the variables that are present in your program. Similarly, in Solidity also, your Solidity programming language is statically typed. Example of a dynamically typed language would be Python. Python is a dynamically typed language. So Solidity is a like object-oriented or contract-oriented high-level programming language which is used for the implementation of smart contracts. And Solidity is highly influenced by C++, Python, and JavaScript. And where do you run your Solidity programs? You run on something which is known as a Ethereum virtual machine. So like Java, Solidity also supports inheritance. It also has libraries. It also has some user-defined data types. And using Solidity, you can create contracts for building your applications, for voting, for like will execution. You can develop your own wallets using Solidity. So this is the basic introduction to Solidity. So we'll see what Ethereum virtual machine is, but today we'll talk about Solidity and see a simple program as to how Solidity works. So if you look at this here, we have a smart contract which has been written using Solidity. So we'll just take an example of a simple contract to see what Solidity is. So before starting with this, I want to explain what Ethereum virtual machine is. So Ethereum virtual machine is a runtime environment which is used for the execution of smart contracts. So whenever you want to execute a smart contract, the environment that you're using is a Ethereum virtual machine. And we know what a smart contract is. A smart contract is a computer protocol which is used to automatically enforce the terms of the contract without the need of any third party. Also, the smart contracts are trackable and irreversible. Okay, so with this information, we'll start with smart contracts. So this here is a simple basic source file of Solidity. So if you look at this here, the first line says that the source code is licensed under the GPL version 3.0. So this is all about that it is a machine readable license for setting, like when you publish something, publish a source code, you have to specify the license under which it has been published. So if you look at the next line here, it says Pragma Solidity and it has a version in front of it. That is Pragma Solidity greater than equal to 0.4.16 but less than 0.9.0. Okay. So it means, now first of all, what Pragma is. Pragma is generally the first line of code within any Solidity file. So Pragma is like a directive that specifies the compiler version which should be used for executing the Solidity file. Okay, so Pragma is always the first line and it specifies the compiler version that should be used for executing your Solidity file. So this is your Solidity file, which is used to write a smart contract. Now it says pragma solidity greater than equal to 0.4.16 and less than 0.9.0. So what it means is that your file is compatible. You can compile this file with version greater than this 0.4.16 but less than 0.9.0. So if you run this Solidity file for any version greater than this, it means that your Solidity file will not run. You will not be able to execute your smart contract. So it says that it will not compile for any earlier version, that 0.4.16, and it will also not work for any compiler that is starting from 0.9.0. So this is always going to be your first line when you are executing your smart contracts. Next, you are specifying the contract. You are specifying the smart contract. The next line says, now your contract in the sense of Solidity is a collection of code and data. Code as in the function that this code will implement, and the data, that is the state. And this code and data resides at a specific address on the Ethereum blockchain. All right. So here you are declaring the, like in Java you have your class type. Here also you say contract simple storage. This is the name of your contract, and the name of the contract is simple storage. And then you declare a variable unsigned integer value, which is stored data. Okay. Now what you're doing is, this is the syntax public set. Set means that you are like modify or retrieve the value of the variable that you are using. So here you are using a unsigned variable stored data, and in this variable you will be storing some value. Okay. So this line uint stored data, it declares a state variable. So uint stored data, it declares a state variable which is stored data, and it is of type unsigned integer. It is of type unsigned integer, and unsigned integer of like 256 bit. And like think of it as a single slot in the database. That is, you have a slot in the database, you can query that slot to retrieve the value, and you can also query that slot by calling this function to change the value. That is, you are storing a value on that slot, on that shared variable. At the same time, you can query it to modify the value. So in this example, we have defined two functions, a set function and a get function that can be used, a set function and a get function that can be used either to store something on your shared variable or to retrieve something from your shared variable. Okay. Now, what exactly this smart contract does is that you have created a variable. Okay. You have created a variable, and in that variable you can store something, and you can also access whatever is stored on that variable. And the thing is that like it is not doing much from like allowing anyone to store an integer number, and anyone in the world can access this integer number. That is, anyone could call the set function again and set a different value and overwrite your number, but the number that was previously set is still stored in the history of blockchain. Okay. So this is a simple smart contract that lets you set a value of a variable, and it is exposing this value for other contracts to access it. It is fine if you don't understand everything right now. We will get into more detail later on. But here we are just trying to give you a like how your smart contract is structured. So you're using the directive pragma solidity to define the compiler which you are using for executing your program. You're declaring your contract, and your contract is performing simple storage. So the first line tells you that the source code is licensed and the license version. The next line specifies that the source code is written for Solidity version 0.4.16 or a newer version of the language up to but not including version 0.9.0. And the reason this is done is to ensure that the contract is like compatible with the compiler version. And pragma are common instructions for compilers that help the compilers understand how to treat the source code. Source code here is this Solidity file. And your contract in sense of Solidity is always a collection of functions and state. You have functions here and you have state variables. So you're employing these functions to change the state of the variable, to change the state of the variable. Okay. And you are declaring a state variable stored data of type uint, and this contract defines the function set and get that can be used to modify or retrieve the value of a variable. Now think of it, now if this was your contract, you deploy this contract on Ethereum, right? You deploy this contract on Ethereum, and as soon as this contract is deployed on Ethereum, it becomes a global contract. Now, what this means is, now here what you are doing is you are just storing something into this variable and accessing. And since the Ethereum is a global machine, anyone can query this to see what is stored here and get a value in return. That is, retrieve a value. Now imagine you can also write smart contracts to say execute a will, to calculate the say like you can say calculate anything, calculate some like banking loans or anything. So you create a smart contract, you deploy it on the Ethereum blockchain, and anyone can use that smart contract by initiating transactions, and the smart contract would be executed. Now here this contract is not doing much apart from allowing anyone to store a single number that is accessible by anyone in the world. Okay. Anybody could call the set again with a different value and overwrite your number, but the number would still be stored as a transaction in the blockchain. And this is a basic smart contract. Okay. Now let us look at another example here. Now it says pragma solidity. Now here you have the symbol and then the version. Now if you want only one specific version to be used, that is if you want a specific version of compiler to be used, you will use this symbol here. That is, this solidity file will only run for version 0.5.0. Again, you create a solidity contract, and your contract is doing just simple things. It is like storing some values in integer variables. It is calculating the sum, and it is displaying the result. That is, you're taking two values, 1 plus 2, and you are returning the result. Okay. Now, there are certain keywords that are reserved for Solidity. Just like Java has certain keywords, here also you have certain keywords, and they are very similar to what you have in Java. You have abstract, you have static, you have switch, and many other keywords that allow you to, you can say, implement your smart contracts. Now, if you want to run your smart contracts, if you want to write your own smart contracts, then you need to use a integrated development environment which is known as Remix. So if you Google Remix IDE is generally used to compile and run Solidity smart contracts. And this is a browser-based IDE. That is, you don't have to install packages, you don't have to set up any environment, you don't have to install anything. You can simply go to Remix IDE, and this will allow you to select the language. You can start creating your smart contracts and start executing them. Okay, so this Remix ID allows you for compilation, execution, and debugging of smart contracts. So you can open this Remix ID on any of the browsers, click on a new file, choose the Solidity environment, and start writing a smart contract. You can also execute this smart contract. Click on the compile button to compile your contract. So we'll see this, but I think we'll see this in the next class now as to how we run a smart contract on the IDE, Remix IDE. So I think I'll stop here for now. If you have any questions, please do ask. Otherwise, in the next class onwards, we'll use the Remix ID to create and execute our smart contracts. Any questions, anyone?